In this video, I will be discussing carbon NMR and DEPT NMR. By this time, you would have already learned about proton NMR. Remember, we learned that there is such a thing as a nuclear spin, and atoms that have an odd number of protons and or an odd number of neutrons in the nucleus will have this quality. So that's why we learned about proton NMR. Another atom that is of significance in organic chemistry is carbon-13. This isotope of carbon will be active in NMR. So let's do a compare and contrast between these two, hydrogen and carbon NMR. First off is the natural abundance of these two atoms are quite different. For example, hydrogen-1 isotope is the most abundant isotope of hydrogen. Naturally, it occurs 99.9%. Therefore, this signal is quite strong when we do the proton NMR. Contrast to this, carbon-13, although is the active isotope in NMR, is only 1.1% of all naturally occurring carbon. Right? So its abundance is quite small. Therefore, it will have a low signal. Because of this, we tend to use a very sensitive receiver coil, or we would need a higher concentration of our sample in order to obtain the spectrum. Another key difference between these two techniques is that, remember, in proton NMR, we have 4 important information we can obtain. We can get out the number of signals it has, or we can, and in each signal, the chemical shift is important. And we can also analyze the splitting pattern and the integration to tell us lots of information. In contrast, carbon-13 NMR is quite limited. You only get the number of signals and where they are, the chemical shifts. So in a sense, this is great because there's less to interpret, but it's quite limiting because you would get less information out of carbon NMR. So let's jump into those features and kind of see why we lose that information. So remember, the carbon-13 isotope is not very abundant. Because of that, it is very rare statistically to have another carbon-13 as your neighbor. So carbon-13 right next to a carbon-13 is statistically very rare. Because of this, we don't see any splitting patterns. However, there is splitting that occurs between hydrogen-1 and carbon-13. Right? The chances of a carbon-13 next to a hydrogen-1 isotope is quite high. So because of this, there's a lot of splitting that occurs. And this splitting makes the spectrum very hard to interpret. To remedy this, we would have to do what is known as broadband decoupling. So sometimes when we see a spectra, you may see that it's labeled as proton decoupled. So let's take a look at an example of this molecule, ethyl phenyl acetate. So on the top, we have here is the proton coupled, just a regular spectrum. And on the bottom is the more useful proton decoupled spectrum. Okay, so let's correlate this and see what happens here. This peak here corresponds to this carbon of this carbonyl. Notice there's no hydrogen around it, and that's why it is not split. It's just one strong signal, so that's fine. As we go along here, you see this mess over here. For example, this is a carbon right next to an oxygen, so it would be around this ppm here. But notice that how many hydrogens is attached to it? 1, 2, right? So you have 2 things attached to it. Remember the n+1 rule, you would get a triplet, which is why you get this triplet here. Okay, now, if you decoupled it, what would happen is that these 3 peaks will collapse back into its one original peak, which is what you get down here. Okay, there you go. That's the difference between the proton coupled and the proton decoupled. This one is a lot more easy to interpret, right? There's so many peaks here, you don't know what is what. Let's do another one. Let's see this carbon right here. How many hydrogens are attached to it? 1, 2, 3. So it should be a quartet, right? So it turns out this is that signal. You see the quartet pattern here. If you decoupled it, it collapsed back to 1. So the more useful spectrum and the spectrum that you need to be able to analyze is this down here, is the decoupled spectrum. And another feature of the spectrum is the chemical shifts. the range in the chemical shifts is from 0 to 200. This is quite different from the proton NMR, which is from 0 to about 12, right? And this is all because the carbon-13 resonates at a different frequency as does the proton NMR. So they have different chemical shifts. And just like in proton NMR, you also have a standard in there, most likely TMS, and that will be set at 0. So we just talked about that each peak represents a unique signal. So let me say that again. Each peak would represent a chemically unique carbon, right? So not unique carbon, but chemically unique. So its environment is unique. So there are carbons that are chemically equivalent to one another, just like how in proton NMR there are hydrogens that are equivalent to one another. So we need to be able to first see when 2, 3, or more carbons are equivalent to another. And this is all based on symmetry, whether you have a mirror symmetry or a rotational symmetry. Okay, so let's take a look at some of these examples. In this first molecule here, notice that these two carbons would be considered equivalent. Anytime you have carbons that are coming off of the same sp3 hybridized carbon, those two carbons would be identical to one another. So for example, if this was another carbon, like 3 carbons coming off the same center, then these 3 carbons would be the same, chemically equivalent to one another. And then this is also a unique carbon because there's no other carbon that has a bromine attached to it. This is another unique carbon, and this is another unique carbon. So in this molecule, there's 1, 2, 3, 4 unique carbons. How about this molecule? Do you see a line of symmetry possible? There's a plane of symmetry here, right? So it reflects perfectly from the left-hand side to the right-hand side if you drew a line here. So therefore, these 2 atoms are the same, these 2 are the same, and these 2 are the same. So there's 3 unique carbons in there. So 3 signals. What about this molecule? Notice that it's very symmetrical, right? So these 2 already we know are similar, and these 2 are similar. But this pair over here and this pair over here actually are identical to one another also. So this carbon is similar to this carbon, and then this carbon is identical to this carbon. So all in all, there's 1, 2, 3 signals in that molecule. How about this fourth one here? Notice that all the carbons in here are unique. This carbon is unique. This is the only one that has 3 hydrogens. This one is unique, even though these 2 both have 2 hydrogens, but this carbon is close to 2 oxygens, whereas this one is close to only 1 oxygen. That's why they're different from one another. So there's 3 signals from that molecule. How about this molecule? I would count this as 1. These 2 are the same, these 2 are the same, and this is unique because there's a line of symmetry you can draw here. So there's 1, 2, 3, 4 unique carbons. How about this one? You can see the line of symmetry here, right? So these 2 are the same. So 1, 2, 3. Again, 3. How about this one here? If you see the line of symmetry is here. So this is 1 atom, 2, 3, also 4. How about this one? You see there's this line of symmetry and also this line of symmetry, right? So with respect to this line of symmetry, these 2 atoms are the same, these 2 are the same, and these 2 are the same. With respect to this line of symmetry, these 2 atoms are the same, these 2 atoms are the same. So therefore, if you combine those 2 symmetries, there's only 1, 2 types of carbon. So there's 2 signals in that molecule. So we just went over and did a lot of examples of the number of signals from a carbon NMR. So that's the number 1 feature from a carbon NMR. The second important feature from a carbon NMR is its chemical shifts, right? Just like in proton NMR, carbon NMR chemical shifts will be very dependent on whether it is shielded or de-shielded, right? Remember, shielded means it has all of its electrons around it to protect it from the external magnetic field. Whereas deshielded, that means it's next to something that is electron withdrawing, and therefore it would feel a greater magnetic field from the instrument, and therefore would have a higher chemical shift. Okay, so the range here is again from 0 to about 200. In this case, I just listed here as 220. Starting from the shielded side here, so if you just have a normal carbon, an sp3 carbon, it would be from 0 to 50 ppm. Moving from 50 to 100 ppm region, you will have carbons that are sp hybridized, like this alkyne, or a carbon that is adjacent to an electron withdrawing group, like oxygen or nitrogen. Beyond that, from 100 to 150, you will have these sp2 hybridized carbons. Remember, this is due to anisotropy, the effect of anisotropy. So anytime you see peaks around here, you know you either have an alkene or it is an aromatic carbon. And then lastly, very high up in 150 and 220, you have these carbonyls, carbons. So again, it's because of the anisotropy effect, and also it is combined with being next to a electron withdrawing atom, in this case oxygen. So let's take a look at an example to see how these chemical shifts play out. So let's go back to our example molecule, this acetate here, and see where these carbons fall. So I've color-coded the carbons here that are unique, right? So there should be 1, 2, 3, 4, 5, 6, 7, 8 signals. Is that true? 1, 2, 3, 4, 5, 6, 7, 8. Excellent. So there are 8 unique signals here. So the easiest one that stands out here for me is this very high chemical shift, around 170 ppm. What could that correspond to, right? This must be a carbonyl, so this must be the orange carbon here of this carbonyl. Next is we have these clusters around 130 ppm. So 130 ppm must mean some kind of aromatic or alkene. Indeed, it is the aromatic of the compound. The next one is this one at 60 ppm. So in this region here, you're either an alkyne or you're next to some electron withdrawing atom. Yeah, so that must be this carbon, the green carbon, is right next to an oxygen. So the last two we have here is around 20 and 40. So they are in this region, so they're just normal sp3 carbon. So they could either be this red carbon here or this blue carbon here. Which one do you think corresponds to this one, the most shielded carbon? Would you be able to guess and make an educated guess that to be the red, right? Because it's farthest away from anything, so it's not being deshielded. Whereas this carbon here is quite close to this electron withdrawing carbonyl group, right? So that would be a good guess. So that's the lowest chemical shift would be the red, and the blue is that last carbon there. Okay, so that's how you would analyze the data from this carbon NMR. So remember, because of the decoupling effect, we only get singlets, so we lose that other information about whether that carbon is attached to other hydrogens, like 1 hydrogen, 2, 3, or 0 hydrogens, which is also important information. However, there is this other technique that will help us do that. It's called DEPT NMR, which stands for distortionless enhancement by polarization transfer. And again, it will tell you the number of hydrogen atoms attached to each carbon. So in this technique, the first thing you do is just take a normal decoupled spectrum. So this spectrum will tell you how many peaks you would have in that compound. Then a special post sequence is used to produce a spectrum. So each sequence is unique, and it turns out that different carbons will respond to each of these sequences quite differently, which gives us this great kind of analytical tool to know what kind of carbons we have. So for example, if you applied the DEPT 135 sequence, you would not get any signal from any quaternary carbons. Quaternary meaning that that carbon is attached to 4 other carbons and 0 hydrogen. However, there will be a signal coming from a carbon that has 1 hydrogen attached or 3 hydrogen attached. And there will be an inverse signal, this is new, an inverse signal if it is a carbon with 2 hydrogens attached. Okay, so that's that sequence. The second sequence is the DEPT 90 sequence. And in this sequence, the only signal that will be seen is the carbon with 1 hydrogen attached. Okay. Finally, we have the DEPT 45. And in this sequence, all types of carbons will be seen except for the quaternary carbon. Right? So for example, if you were this orange carbon, what kind of sequence would you see? This is a quaternary carbon, right? So therefore, you should see that in DEPT 135, 90, and 45, you should see no signal. Yeah? How about let's look at this green carbon. This green carbon is CH2. So you will see it this sequence, where it says negative signal in 135, no signal in 90, and positive signal in 45. How about this one? Oh, this one should have been a CH3. Oh, typo there. So this is a CH3, so you should see signal in 135, none in 90, and signal in 45. Right? So let's do an example. So we have here this ketone molecule, 2-butanone. First, we see that we have the carbon decoupled spectra. There's 1, 2, 3, 4 signals. Remember that there's always going to be a signal at 0 or around 0, which is a standard, right? So that's the TMS. Okay, so let's analyze this here. Let's go across this signal here. This peak here, again, we should note that is above 200, so it must be the carbonyl peak, right? And that must be B right there, the carbonyl carbon. But also to double check with the depth, remember there's no hydrogens attached to it, so that's why it's very, very silent in depth in all 3 sequences. Okay, so let's move on to this carbon here. So this carbon in the 135 sequence is negative. In the 90, here's the thing. In the 90 is very tricky. Even though you see these small signals, it's a bleeding of signals from the other spectrum. So always be cautious when you see these smaller peaks, all right? I wouldn't trust it so much in the 90. In this case, this is not a signal. Okay, and you get that, you will get the hang of that as you do more of these, whether it's something as a signal or not. Okay, I would also always assume if it's small like this, in 90 it's not a signal. All right, so let's go back here. So we got 135 has a negative signal, no signal, and then positive signal. So down, nothing, up. That must be a CH2. So carbon C here is a CH2. So in this molecule, which one is a CH2? It must be this one. This is the only CH2. Right? And lastly, we have 2 CH3, so they will have the same signal, right? So A and D would be up. I mean, not up. Up here, nothing here, and up here. So is that right? CH3, up, nothing, up. That's right. So there you go. There we have it. This is our analysis of our carbon depth carbon NMR. All right, so that's it. So to summarize, what are the important things you need to know about carbon NMR? So in carbon NMR, there are 2 important information you need to be able to analyze. The first is the number of carbon signals you have. And the second important feature is the chemical shifts. know where a certain carbon will fall depending on its chemical environment. And lastly, in carbon NMR, there is a special technique called DEPT NMR, which gives us the information about how many hydrogens are attached to a particular carbon.